All right, here's take one of project one for ME304. So this is a strain rosette to principal stress problem. I'll read the problem statement. The strain rosette shown is used to measure the strains on a structure made of AISI 302 stainless steel. Gauge 1, shown here, reads minus 300 times 10 to the minus 6 inches per inch. Gauge 2, shown here, reads 200 times 10 to the minus 6 inches per inch. And gauge 3, shown here, reads 425 times 10 to the minus 6 inches per inch. And we are asked to find sigma 1, sigma 2, and tau max, which are the principal stresses, and tau max. Report your answers in KSI. For the stress transformation step, please explain how to use Mohr circle and not the stress transformation equations, which I will talk about here. So shown here is basically the game plan to solving these types of problems. We're going to start with a strain rosette or strain rosette values, and we use the strain rosette equations to turn these values into a state of strain for our material. Once we're here, we can take two approaches. The one we're going to take in this example is from the state of strain. We're going to use generalized Hooke's law to turn our state of strain into a state of stress. From here, we will use Mohr circle to analyze the principal stresses from the state of stress. So let's get right into it. So what we'll do is basically assign a strain for each of these. This can go away. And there's the strain rosette equations. All right, get out of here. So we have, if you noticed, rosette number 2 or gauge number 2 is on the x-axis, so we will label that our strain in the x is equal to whatever value is on strain 2, which or gauge 2, which is 200 times 10 to the minus 6 inches per inch. So we have one of our components to our state of strain already pretty much identified. So now we will use the rosette equations to find two equations, a system of equations, which we will solve for our two variables that we need, which are going to be EY and gamma XY. So here it's called strain B, but we will call it strain 1. So strain 1 is equal to EX cosine squared of theta 1 plus EY times sine squared theta 1 plus gamma XY cosine theta 1, and then this is multiplied by sine theta 1. So we will now plug in for the values. We're given this gauge value, which is up here. So it will be minus 300 times 10 to the minus 6 inches per inch is equal to, this won't fit here, so we're going to do it lower. So minus 300 times 10 to the minus 6 inches per inch is equal to strain X, which is already given, or we already found it, identified it. 200 times 10 to the minus 6 inches per inch. And then cosine squared of theta 1. Theta 1, sorry if I didn't make this clear, theta 1 is equal to minus 75 degrees because it's clockwise from the x-axis. Theta 3, which we will use to find strain C, is equal to positive 75 degrees. So that's what we will use in the strain rosette equations. So cosine squared of minus 75 degrees plus EY, which is not yet found out, we're going to solve for it, multiplied by sine squared minus 75 degrees plus gamma xy cosine minus 75 degrees and sine minus 75 degrees. All right, so here is one of our equations in our system of equations. So we're going to go ahead and simplify this for now. So it's still minus 300 times 10 to the minus 6 inches per inch is equal to this value here is, well, we can calculate it in the calculator. So we're going to do cosine, is this clear? Yes, cosine of minus 75 squared, we get this value, multiplied by 200 times 10 to the minus 6. Here we go, 1.33, 1.34 we'll call it. Yeah, so 1.34 times 10 to the minus 1, 2, 3, 4, 5. And then plus EY minus sine squared 75. Let's see what that is. So, or no, multiply by, sorry. So sine minus 75. Oops. Enter, squared, enter. All right. So to get the decimal value, 1/2 plus 2 divided by 4. So 0.933, we'll call it, times 0.933 plus gamma xy times, which cosine minus 75 times sine minus 75. We have negative 1/4, we'll call that minus 0.25. So here is one of our equations in our system of equations, and it's simplified and ready to plug into a calculator. So now that we know these values, when it turns into positive 75, it'll be the same value. Same here. This is the only one that will change when we use equation or theta 3 to find strain 3. So let's go ahead and do that. Here's the equation for strain 3. So strain 3 is equal to strain x, which is 200 times 10 to the minus 6 inches per inch, times cosine squared of, okay, we'll start with writing out the equation. So strain 3 is equal to strain x cosine squared theta 3 plus strain y sine squared theta 3 plus gamma xy cosine theta 3 times sine theta 3. Okay, now let's plug in. So theta 3 is, or sigma, or strain 3, sorry, is here on gauge 3, 425 times 10 to the, I hope you guys can see this, yes, okay, 10 times 10 to the minus 6 inches per inch is equal to strain in the x, which is already given, so 200 times 10 to the minus 6 inches per inch multiplied by cosine squared of 75 degrees, positive now because it's positive here, plus strain in the y times sine squared of positive 75 degrees. I think my pen is dying on me, so I will switch that out. Then we have plus gamma xy cosine of positive 75 degrees times sine of 75 degrees. So like I mentioned, this value here will not change to the negative 75 value because it's squared anyways. So we basically have the same decimal here and here. So to simplify this, we have 425 times 10 to the minus 6 inches per inch, which is equal to 1.34 times 10 to the minus 5 plus strain in the y times 0.933 plus gamma xy cosine 75 times sine 75. The only difference is this is going to be positive, so it's 0.25. here we have our second equation to the system of equations. So these two will be plugged into a calculator on Wolfram Alpha, because this has now become an algebra problem to solve for sigma y and gamma xy, or sorry, strain in the y, gamma xy, strain in the y, gamma xy. We're going to be solving for these variables. So after I plug this into a calculator, we have gamma xy is equal to 29 over 20,000. Yes, you guys can still see, which is equal to 1.45 times 10 to the minus 3 radians. And then we have strain in the y is equal to 11 root 3 minus 18 over also 20,000, which is equal to, I'm going to switch this pen out real quick. RIP pen, which is equal to 5.26 times 10 to the minus 5 inches per inch. So here we have our states of strain. So you might be asking, where's strain in the x? It's already up here, if you recall. So here's our strain in the x, strain in the y, gamma xy. So we now have our state of strain. So if we look back, we are now here. We went from here to, from the strain rosette values to a state of strain. So next up, we need to use generalized Hooke's law to find a state of stress out of our state of strain. So I will be using a new paper. I will be using the back of this paper. All right. So now we need to find our generalized Hooke's law equations, which I believe are on the back of this paper. That is wrong. Here they are. So disregard the rest of the gibberish around here. Here is our generalized Hooke's law equations, which we can write down over here to have at hand. Sigma x is equal to E modulus of elasticity, 1 minus this variable here, strain in the x plus this variable, e to the y. If I knew the name, I should probably find out the name of this. I will edit that into the video. So here we go. Sigma y is equal to modulus, Young's modulus, 1 minus that squared, strain in the y, plus here strain in the x. Tau xy is going to be equal to G, which is modulus of rigidity, times gamma xy. All right, so we need to find this variable here. The way we do that is in the textbook we are given, or we look at our material, which if we recall is AISI 302 stainless steel. So we look up modulus, or your modulus of elasticity, aka Young's modulus, which is equal to one second. Okay, 28,000 KSI, and modulus of rigidity, which is equal to, or defined as, 10,800 KSI. And our equation to find this variable here, weird V is equal to E over 2G minus 1. So if we plug these values into this, we have V is equal to 28,000 KSI over 2 times 10,800 KSI minus 1. We calculate that. We have 28,000 over 2 times 10,800 minus 1 gives us 0.296, we'll call it. Which is going to be important when translating our state of strain to a state of stress. So let's go ahead and do this now. Okay. So if we recall, I'm going to rewrite these down in the back of this page. So we have strain in the X was equal to 200 times 10 to the minus 6 inches per inch. Strain in the Y is equal to 5.26 times 10 to the minus 5 inches per inch. And gamma XY is equal to 1.45 times 10 to the minus 3 radians. Alrighty. Easiest one to find is tau xy, so let's do that first. Tau xy is equal to G, which is 10,800 KSI, multiplied by gamma xy, which is 1.45 times 10 to the minus 3. Oops, this is a 3. Yes, to the minus 3. That'll give us a strain in the, or shear in the XY of 15.66 KSI. And then we have, we'll go ahead and do sigma X next. So we have, yes, okay. Sigma X is equal to E, or Young's modulus, 28,000 KSI over 1 minus V squared. 1 minus, we said it was 0.296, 0.296 squared, multiplied by strain in the X here, 200 times 10 to the minus 6 inches per inch, plus the V variable, 0.296, multiplied by strain in the Y, 5.26 times 10 to the minus 5 inches per inch. So when you solve this out in the calculator, you get a value of 6.62 KSI. Like Dr. Lehman says, this has become an algebra problem. To solve for this, just multiply it out into the calculator. You can trust me, 6.62 KSI. Here we have sigma in the Y, strain, or yeah, stress in the Y. Young's modulus, we're using this equation now. Young's modulus, 28,000 KSI over 1 minus V squared, 1 minus 0.296 squared, multiplied by, now we have stress in or strain in the Y first, not being multiplied by that, so let's do that. Strain in the Y, plus, now we have 0.296, which is here, our V variable multiplied by strain in the X now, which is 200 times 10 to the minus 6 inches per inch. Again, this has become an algebra problem. Plug this into your calculator and you should get 3.43 KSI. Okay, so let's backtrack. So we went from our gauge readings, which was 300 in per inch, 200 times 10 to the minus 6 inch per inch, and then 425 inch per inch. So we went from here, which was the strain rosette gauge readings, and we turned them into a state of strain, which we have here. Using the system of equations that we got from the rosette equations. And then from our state of strain, we used generalized Hooke's law to go to a state of stress, to translate to a state of stress. So from generalized Hooke's law, by the way, this is generalized Hooke's law here. From generalized Hooke's law, we were able to take our state of strain and turn it into a state of stress, which we have now here. Awesome. So now it gets to the good part where we get to draw circles and find the principal stresses. So let's go ahead and do that. What we will do, right, so if you didn't get that, so now we will use more circle. So we are here now. We will use more circle to find our principal stresses now that we have our state of stress. So I'm just gonna rewrite on this new paper our state of stress. 15.66 KSI is tau xy. Sigma x is equal to 6.62 KSI, and sigma y, stress in the y, is equal to 3.43 KSI. All right, so let's go ahead and draw our axis so that we can draw our circle. Good enough. Well, I should have actually just drawn the positive side since both of our stresses are positive. You'll see what I mean when I draw the circle. So we no longer need this. Now what we need is how do we make a more circle analysis? Which there are clear steps in doing so. I just need to find them, and they are here. Alrighty, so let's just go over the game plan again real quick. So begin with a known state of stress. Here it is, we just calculated that. Plot these 2 points. So I'm actually gonna draw down these points here. So point 1 is going to be regular positive stress in the x, and then for your other variable you're going to do minus tau xy. So let me label our axis here. So here is stress, here is tau. All right, so or tau xy. No, just tau. Anyways, so sigma x minus tau xy, sigma x 6.62 KSI minus tau xy, so minus 15.66 KSI. So that's our point 1. Point 2 is sigma y and then positive tau xy, or just regular tau xy, which is 3.43 KSI, comma, positive 15.66 KSI. Alrighty, we have our 2 points. Let's go ahead and plot those. So stress in the x, tau in the y. Let's do 6.66. We'll call that this spot here. 6.62, sorry, KSI. And then with minus tau xy, so minus 15.66. This is not at all drawn to scale. If it was, it would be way down here. So minus 15.66 KSI. And then we have 3.43, which is, we'll call it halfway through, not drawn to scale, like I said. I just want to draw it so that it's distinguishable. here we are, 3.43 KSI. Like I said, I should have drawn this on the positive axis, which, to be honest, it's not too late to do. So I'm gonna go ahead and do that. So, oops. All right, so 1 second. Yeah, okay, cool. So let's just go ahead. Now that we know that it's only going to be on the positive axis, let's go ahead and redraw just the positive axis. It'll give us a better analysis. So what did we have? We had a positive 6.62 KSI. So we had a positive 0.62, and then we had a 3.43. I'll just redraw the points that we have. 0.6162. Alrighty, so here we have that, and then it's plotted with minus 15.66, minus 15.66. So we'll call it here. And then this one is positive, so it's plotted against positive 15.66. So we'll call it right about here, 15.66, and then we'll call it here. Okay, so step 2 is done. Step 1 is done. Draw a diameter, which means connect the 2 dots. So let's go ahead and do that. And I notice now that this is going to be a huge circle, which is okay. So here's our diameter. So step 3 is done. Look at the center. So we need to find out what this point is here. How do we do that? We find the average between these two, which is 6.62 plus 3.43 divided by 2, 5.025. We'll call this point here 5.025. Oops. Gotta make sure it's in the frame. Okay. So we found the center, which allows us to do some triangle analysis for the radius. So, actually, step 5 says to draw the circle, which is going to look something like this, but a lot more circular. Anyways, pretend that's a good circle, and let's carry on. Draw the circle, find the radius. So now we will use these two values and this value to do a radius analysis. If you notice, this here is a radius. So we need to find this distance and this distance here. This distance here is already given, 15.66. And then, if I didn't explain it well, we're going to use Pythagorean's theorem once we find these two values to find r, which is the hypotenuse of this triangle. To make it more clear, this here is the triangle I'm talking about. Okay, so what's the distance here? It's going to be 5.025 minus 3.43. 1.595, we'll call it 1.6. Alrighty. So Pythagorean theorem states that R is equal to, can you guys see that? I believe so. So R is equal to square root of the components squared, which we have 1.6 squared, plus the sum of the components squared, sorry, plus 15.66 squared, which gives you a value of, so we already have 1.6, so squared plus 15.66 squared. Find the square root of this, gives us 15.74. Our radius is 15.74. If you notice, when finding tau max, it's just going to be up here wherever the circle touches the top. And if you will notice, this is a radius. So this is R here all as well. So it is given that tau max is equal to the radius, which is 15.74. So I just wanted to point that out, and 1 out of 3 of our principal stresses, if you want to call them, is already found, or our shear, actually, our max shear is found, which is one of the solutions. So you already have one of the solutions done. Next, I guess we were already on to step 7. Identify sigma 1, sigma 2, and tau max, etc. just means, or I'm sorry, yeah, just tau max. So now, our sigma 1 is going to be here, or I mean our sigma 2 is going to be here because it's less, and our sigma 1 is going to be over here. Maybe this is negative, maybe it's not. Remember that our circle is not drawn to scale. Why don't we find out? So we know what the center of our circle is. The way we find our sigma 1 and sigma 2 is we add or subtract the radius. So to find sigma 1, we're going to use our center value and add a radius, because if you notice, this is a radius. And to find our sigma 2, we're going to subtract the radius, and if you notice, this here is a radius. So let's go ahead and do that. We have our radius here, 15.74. Let's add 5.025. So we have our sigma 1. Sigma 1 is equal to 20.7, we'll call it 77 KSI. Sigma 2 is equal to 5.025 minus the radius, so we'll call it 5.025 minus 15.74. If you want to write these equations, I guess, sigma 1 is equal to 5.025 plus R. Sigma 2 is equal to 5.025 minus R. So sigma 2 is equal to minus 10 point, we'll call it 72 KSI. So here are the solutions to the problem. We have tau max, which we found here. Sigma 1, sigma 2, your principal stresses. So one last time, we'll talk about the approach that we took and just sum it all up. So yes, these are your final answers here in a different color. So let's go ahead and, like I said, go over what we did. So if you recall, we started off with our strain rosette gauge readings, 1, 2, 3, oops. Okay. So we started off with our gauge readings, 1, 2, 3. And we went from there and we found a state of stress using the strain rosette equations, which are these are from my notes, by the way. Here. Okay. So gauge readings we're here. Strain rosette equations, which are these, to find a state of stress, which stress in the x, or I mean strain in the x, strain in the y, gamma xy. We're here now. We used generalized Hooke's law to go from a state of strain to a state of stress, shown here, generalized Hooke's law equations, and here is our state of stress. So now we used Moore's circle, which the steps again, 1 through 7, shown here. Pause the video if you'd like to read those. And that took us to, or from, our state of stress, which was these values here, which I already explained. And it took us to our principal stresses, which are sigma 1 is equal to 20.77 KSI, sigma 2 is equal to minus 10.72 KSI, tau max is equal to 15.74 KSI. And you are very happy because you are done with the problem. Thanks for watching. That should be it.